today, just to give you a preview of what we need to talk about today, we'll finish up our conversation about light, mainly to talk about the instrumentalization of light, so telescopes and spectroscopy, which are kind of our two main tools in astronomy. So we need to make sure we understand those. The next thing on deck really is to start going through the solar system and looking at every single major object that we have in it. So I think the best way to do that is actually to take a 30,000-foot view of the solar system first, and then we'll kind of work our way from the interior outward after that at a really luxurious pace. So that should give you guys a chance to start thinking about the story of the solar system. And in general, I think it's really important that we start thinking about everything that we're doing as stories, right? All of these theories as stories, not meaning that they're not valuable, but the fundamental unit of knowledge seems to be the story. It's how we remember everything. And so I want to start comparing stories of the solar system eventually. And I don't know that we'll get to that today. Maybe we will. Like I said, there's a few more nitty-gritties we need to understand technically before we can start looking at these things, because everything that comes next in terms of the stories comes to us by way of spectroscopy and telescopes. So if we don't understand what's going on with that primary data, then it's difficult for us to start interpreting it on the back end. So I know we had a pretty wild conversation about light last time. I'm curious what questions remain. I will go over this paradigm in a minute, in a bit more depth, but I'd love to hear from you guys if you've had any thoughts since you've been away. Yes, David.
I never really thought of atoms like being so connected with just how light travels itself. The fact that like it takes like two atoms and one of them kind of like teetering, like emitting a bunch of power to the other one, kind of like a bolt of lightning from one to the other. And like the way you described it with like atoms, that they're like just appearing with like light. It's like the atoms are already there. It's just they're kind of like shooting at. I guess I don't. My way of describing it's not the best, but I just thought that was interesting. I never knew atoms and light interacted that way.
It is really interesting. I think interconnected is a good word to think about it. I actually had a really cool podcast this morning with a dude who's using this same idea for gravity. So he's trying to use, so the technical name for what we were talking about is the transactional interpretation of quantum mechanics. There's lots of attempts to explain how quantum mechanics gives the very bizarre answers that it gives, how these photons can go through both slits at the same time and so forth. And one of them, the one that I've kind of been advocating, the most mainstream conception of it is called the transactional interpretation. And so it was very interesting. This dude is a physicist. He's in Switzerland, I believe. His name is Andreas Schlatter. I'll share that podcast with you guys when it comes out. But it was really fascinating to see that same idea applied to gravity as well, because gravity, of course, also involves two atoms, right? You're sticking to the floor right now for some reason. And there's a lot of really interesting parallels between light and gravity. As far as we can tell, as much as we understand about gravity, it also seems to have some wave-like nature to it. You guys may have heard of these LIGO, these gravitational waves and so forth. They're also transverse waves, and you would be hard-pressed to find transverse waves in the universe other than light and gravity. It's a very strange kind of oscillatory wave. It's not this nice longitudinal compression thing that you see in sound and in waves and materials otherwise. So there's something really special going on there. And so I expect to see more development of a transactional theory of gravity eventually. So yeah, that's really cool stuff. And if you guys are interested in it, we've done a number of conversations. I'm actually, somebody asked me, I can't remember who, I think it might have been you, at the end of the last class to put together maybe some sort of playlist of some interesting folks who are exploring this stuff on YouTube and so forth. And I'm going to try to do that and stick it in the syllabus. I just haven't gotten to it yet. But I'll get that together too, because I think that's, there's a lot of people working on these ideas, and there's a lot of people communicating them also. So oftentimes scientists, the people behind the telescopes aren't necessarily the best talkers. And so there's some really good channels for people synthesizing what's going on with all that. Cool. I'm glad you were thinking about that. Anybody else take home any thoughts? Think about anything I can just pick on people otherwise. Yeah. Rolando, yes.
Our talk about radiation was interesting. I never thought that it was like light.
Hmm.
Kind of brings back that idea of how words are kind of muddled.
Yeah.
It always felt like some other thing. So that was interesting.
Yeah, it is really interesting. And it's interesting how words inform how we think, too. I think that the older I get, the more I realize that it's kind of restricts our way of thinking about situations. I think the word particle is one of the worst words in all of science, actually, and physics, I should say, just because, of course, we're not actually talking about little motes of dust. We're talking about events. And the minute we start treating events like physical objects, we get really confused. Even the smartest people can get confused when we start doing that. So yeah, I'll keep an eye on that because that's an example that pops up over and over and over again. I'll see if I can bring some more examples to bear. Yes.
Really interesting. You were talking about the, I forget exactly what it was called, but it was like when the black body heats up, you can like measure its temperature by the color,
Yes.
light that it gives off. How that is currently how we measure the temperature of distant stars, or both stars in general. They're all distant. Anyways, and how that's like potentially very problematic because they might not be like a black body. So then here we're at like we're talking gas here and how they have the corona around them, which might also influence the color that they give off. Anyways, just found that really, really interesting.
Yeah, I mean, they might, so all solids and liquids give some degree of black body spectrum. The temperature is not what I'm so much concerned about. I think I confused this a little last time. I'm glad you brought it up because I want to clarify this a little bit. So the temperature might not be true, but that's not the biggest problem. So in the sun, for instance, this isn't a class about the sun, so we can't waste too much time on it, but the sun has convection in it that's apparent. It looks like it's bubbling, sort of like a pot on your stove or something like that. Now, in a black body experiment, a true black body experiment like the ones that we're talking about here, there's no other source of dissipation of that heat energy other than the rays that are coming from that black body. So anytime that you have another way for energy to be dissipated, like in convection, for instance, where there's motion that's attributed to something else besides the light, your temperature is going to be artificially, decreased, right? Yeah. So, okay, that's a problem. The main problem, actually, and this is a bit unfortunate because I don't think we really get into it till next semester, but in terms of the actual equations for this, but a huge portion of next semester is devoted to how do we know how far away something is in astronomy, right? So I think did we talk about parallax a little bit in this class? Close one eye, close the other. Okay, that method works for things that are pretty close to you. It does not work for things that are much beyond our solar system. And so what do you do to try to determine how far away something is? Well, you have to make, first thing you can do is see how bright it is. And this is sort of like, you're walking down a country road at night and there's a headlight coming at you. How do you know if it's a semi-truck or a bicycle, right? It's very difficult, actually. Hopefully you can hear something about it and it sounds like a bicycle or it sounds like a semi-truck. So then once you know the size of it, then you can say how far away you think it is, right? Now, you have to make some assumption about the size of it up front. This is where things get really tricky because what we do is we say, well, this star has a particular gravitational effect to it. It's dragging other stars around in a certain way. Therefore, we know the size of it. Now, if we know the size of it, and we believe that that brightness is entirely dependent on size, then we might make the mistake of thinking that that star is really far away or really close or something based on that assumption. Now, how would we mess that up? Here's where the black bodies come in. If that structure, right, if the surface of that sun is not this actual perfect black body that, say, it seems to be in our star, right? And it has this really nice lattice, which is basically putting out all of that heat energy forward. but say that the lattice is somehow different. And I made the example of soot versus diamond, right? You have two materials made out of the same atom that have very different optical properties to them. And so if we neglect the actual arrangements of the atoms and we just think about the type of atom alone without the arrangements, then we might miss some really important information about what contributes to brightness. Therefore, we could mistake how far away something is, we could mistake how big something is, and this could have devastating consequences on our map of the universe as a result of it, and the conclusions that we draw. So, case in point, there's these really interesting stars that we'll deal with next semester called white dwarfs. And white dwarfs are weird because they are very dim stars, but they have a lot of gravity associated with them. And so, since we are unable to make any story up right now for why in the world something would be dim without it being small, we assume that these white dwarfs are small as a result of that. So, what I'm trying to say is that the way that we think about the sun right now is that it has no lattice structure to it at all. We treat it as this strange thing, which is called a plasma, which is a gaseous plasma in that sense. It has no crystal structure to it. It has no structure at all, actually. It's just the atoms are kind of dissociated and everywhere, and there's nothing to it. That would be a reasonable story if it weren't for the fact that the sun clearly has a black body structure, just like solids and liquids do when they're heated. And so what I think that we're coming to realize, at least a number of scientists are coming to realize, is that the sun must have some lattice structure, and that lattice structure is going to give it optical properties which are going to determine how bright it is. And so we need to start thinking about these bodies when we look at them, not just in terms of their size, but also, when we think about their brightness, we can't just think about brightness equaling size anymore. It's not so simple. And I'm sure it's a problem that can be solved, but the results of course, thinking that white dwarfs are small in size, but heavy, is that you have to create new forms of matter to account for how in the world you would have something so gravitationally massive, but so tiny in radius, right? It's dim. So how in the world does that happen? Well, it might not require a new form of matter if you consider that the lattice structure of the material in that star is just in a different state. It could also lead to really cool explanations for pulsating stars, and honestly, God knows what else when we look out at the universe. So it's a really important phenomenon. It does obscure the temperature to some extent, but that's probably not the biggest problem. Other thoughts? Yes.
It just kind of occurred to me, like, it is weird that each element, at least when I was taught, like, each element has a bright light spectrum. So how the hell do stars have all of them?
They don't have all of them. They have a lot, yeah. Oh, exactly. Yeah, they do have the continuous spectrum. It's a really big problem. The deeper that you get into all this stuff, the more obvious it'll strike you as the biggest problem in all of astronomy, actually, because so much is built upon it. And a lot of this we deal with next semester. I keep having to defer to that because we're supposed to be really focusing on the planets in this class, but it's hard to not talk about this problem because it's so central. And especially, we're going to start talking about the Big Bang Theory next semester. And one of the let's say there's two main pillars of the Big Bang. One of them is this cosmic microwave background radiation. It is also a black body spectrum, which, for the same reason, casts serious doubt on it being this plasmatic gaseous event of recombination at the beginning of the universe. Yeah, it's a serious issue, but I think that it's an issue that can only help us understand the universe better as we move forward. Yes. Remind me your name again. Remind me your name.
How big can a star be, right?
I don't know that number off the top of my head. Wait, you said James?
Yeah.
I don't have you on my list. That's interesting. Okay. You say Alan?
Alan,
yeah. Nope. Interesting. All right. I'll put you in here and we'll catch you up. I've seen you here, so don't worry. All right. In terms of the size, yeah, I mean, so this requires us to talk about the life and death of stars, right? There's instabilities that can develop. They're very complex beasts. We'll have to, I hope you stick around next semester because we'll tear it apart. But you always are fighting, you're always fighting between different pressures in a star, between the different modes of fusion and radiation pressure and gravity, essentially. But they get huge, like gazillions of times the size of our star. Let me see if I can find a comparison of some of these blue giant star. Oops, my keyboard switched to Russian. My wife speaks Russian. Blue giant star versus our sun. Let's see if we can find a picture of it really quick. Yeah, I mean, really, really preposterously large. Let's see if I can find a good comparison. All right, these are all terrible. But needless to say, hundreds, thousands of times, right? Much, much larger. And of course, many of these, which is interesting, is that they're blue, so they're thought to be very, very hot, right? But the question is, are all large stars hot? And that might be able to solve some really interesting mysteries for us too. There's a lot of unaccounted for material in the universe. It's, you know, this is largely cloaked under the banner of dark matter right now. There's stuff holding things together that we can't see, so what's going on with that? Again, if the brightness of stars has to do very much with the material properties, the arrangement of the atoms in its surface and so forth, it could be obscuring a lot of cold stuff that's really big and chunky out there too. Remember, we can only see stuff that's bright in the sky. This is also a really interesting filtering problem with astronomy, right? You can only see what you can see, right? So you only see the things that are giving off light. You don't see the things that aren't giving off light. And you know, we'll probably touch on this some more later, but there's a real crumbling line between planet and star called a brown dwarf. You guys heard of this term before? So there's a, you know, I like to explain it this way, that the definition of a star is one that can essentially fuse normal neutral hydrogen, right? Not like a weird isotope of hydrogen, but just normal hydrogen. It can do regular fusion. So that's what a star is, a body that can do that. However, the composition of a star and the composition of something like Jupiter is almost the same, actually. They're made out of basically the same stuff in similar proportions. Now, if you start piling hydrogen and helium onto Jupiter and you keep piling it on, at some point it's going to get heavy enough that it does do that kind of fusion that makes it a star. Now, the interesting sort of thought experiment here is that there's a threshold there where if you add it's like the straw that broke the camel's back. If you add a single atom onto one of these super Jupiter brown dwarf type planets, at some point you add one atom onto it and boom, it's a star. Likewise, you take one atom off of that star and it's back to being a brown dwarf, right? So there must be bodies out there that spend some time as both, actually. It's just logical, right? If there's a threshold that separates them, then it must be a situation where you can have stars. Gosh, we're really into next semester's territory, but you can have stars that move both ways, let's say, on that ladder. Yeah.
I got distracted, but the question was, how big can a star be, right?
Yes. Did you figure it out?
It says there's one called UY Scuti. It has an estimated radius of 1.188 billion kilometers, and it fills the center of our universe, its outer orbit within Jupiter.
If it was at the center of the solar system, it would reach all the way to Jupiter. Wow. All right. So unimaginably large, yeah. Yeah, that's pretty crazy. I mean, you take it with a grain of salt, though. So that's assuming that a lot of our distance measurements and stuff are correct, too. But I would imagine that no matter what, things can vary in size quite extraordinarily. And it seems like our star is definitely on the smaller end of things. Although it turns out most of the stars are on the smaller end of things. So it's not particularly unusual in that sense. Yeah, good food for thought. Anybody else want to chime in? Thoughts from last class? Sarah, right? It's all good.
But I was watching the videos and I saw the one about the expansion theory. And I did call everyone that was important to me and I did tell them about it because I felt so strongly about it. And it really,
Which one was this? Can you remind me?
it was one of the YouTube videos that you posted with the direct
Oh, it was a podcast. Okay, yeah. Okay.
expansion theory.
Oh, yes, yes.
And it just makes me feel so like, yeah, it is kind of dumb to say, no, you don't understand. All of the land was one big block and then the rest of it was ocean. And I'm like, wait, that is kind of really dumb. Also, none of the pieces fit together. Wait, there has to be another explanation. And I think you really drove it home talking about the buoyancy of and like the different like geysers and everything. And I just,
Was this a short 10-minute video?
I think it might be
Okay. Yeah, we made a short little video.
But I do not recall the explanation about like earthquakes and tectonic plates. That was the argument. I was like, I know he mentioned something about it. I was like, I'll just send you the video. I don't know.
Yeah, I think we're gonna get into that soon. Let's not do that right now because it's too crazy to just brush over really quickly. And so, just to preview that for everybody, people aren't aware of this, but back in the 1950s, there was two theories of how the continents came to be where they're at, and they were very seriously entertained, both of them. One of them is the one that we all know today, which is that there was this Pangea thing on one side of the Earth, and it split apart, and the continents drifted on these convection belts to their present location. This is called continental drift. The competing idea for that was that the Earth used to be a lot smaller, and that if you shrink the Earth, all of the continents fit together perfectly like puzzle pieces with a few missing little darts, and that you can basically, if you have a mechanism for how the Earth grew, then you can explain the present position of the continents. And so we'll pick apart those two different ideas and see which one makes most sense to you guys. But needless to say, that requires a great deal of exposition, so we'll go through it. It is quite interesting, though, especially because most people don't even know that that was like a legitimate scientific theory like 75 years ago, something like that. Okay. Let's do, I need to call on some people who I didn't get through last time. Some of you have already probably dropped the class, so forgive me. Is Alex here? No. How about Caleb Davies? How about Caleb Johnson?
Yeah, I'm here.
Very good.
There wasn't really anything else that stood out to me.
Okay. Do you remember anything whatsoever?
I mean, I remember like talking about light, obviously. But
All right. Well, take some notes this time. Let's see here. How about Carter? Are you still in this class? No, probably not. How about Gabriella? No, probably. Some of these people who have never been here are probably never going to be here. How about Heidi? Are you here? Okay, cool. Any thoughts? You said you missed it, yeah. Okay, well, that's cool. Send me an email. How about Jaden? Oh, you already talked, yeah. All right. How about this person's probably not here. Joe, you're not in our class anymore. How about Kat? You're not in our class anymore either, I bet. How about Keegan? Are you in our class anymore? No. How about Levin? Awesome. Yes. Any thoughts?
Just wondering if we're going to go over fluorescence.
Maybe. We can, though. But we have to talk about ionization and stuff like that. I think we'll have time for that. I'll keep it in the back of my head. It's not quite the time for that right now, but I think we can do it. Yes. Cool. All right, I'm gonna just keep going with things then, because, yeah, we have a lot to catch up on, and I want to get around to the solar system, which is really what we should spend the back part of this semester dealing with. So, if there are no more thoughts or questions about our general, any last thoughts or questions, things that are bothering you? Yes, please.
Just like the idea of like there needing to be two atoms, there needs to be a receiving atom as well as the atom that's actually making the wave happen. And I was thinking about it, I was talking to my girlfriend about it too. Like logically, it just doesn't make sense. Like if fell down and there wasn't anybody here, like, there needs to be some sort of thing to actually absorb that weight, you know? I mean,
Yeah, even empirically speaking.
yeah, so, like, it only makes sense that, you know, you need two atoms to actually, like, understand what the wave is because it's coming from almost an extension of itself. So it has some understanding of what that liquid is.
Yeah.
That's holding it together.
Yeah, how do you think we got this far without? I think personally it has to do with calling the light these particles of light, these photons. Because if you think of it as a particle, you can just throw a bowling ball or shoot a cannonball off into space, right? It doesn't need a partner. But it's unfortunate because I think that, yeah, it obscures probably a better understanding of what's going on. And, you know, this really comes to a head next semester more than anything because the second, a huge part of this cosmology, right, this idea that we have of the birth of the universe and so forth comes down to interpreting what these light signals mean, particularly this microwave background radiation and so forth. And if you know, a lot of these arguments get a lot more shaky when you start considering the partners involved and so forth. Yeah, it might matter more later. Yes, Doris, is that right? Okay.
That was definitely one of the things that I was thinking about.
I mean, you mentioned a lot of things here. You know, they sound pretty crazy on their face, but there are some really bizarre studies about this kind of thing. Water, too, look, water is kind of the dark matter of biology. 99 out of 100 molecules in your body is water, first of all. Not necessarily by mass, but just if you count the actual molecules in your body. So, and you know, I actually did my PhD studying water molecules, doing very, very strange things. I won't bore you with the details of that right now, but needless to say, water does a lot of work in the body. Water that does work it doesn't really get credit for. We often think about, you know, proteins doing this, fats and all of these different molecules, but the reality of the situation is that they're in some sense given their shape by water. And the degree to which water is interacting with light, which is interacting with folding all of these proteins and so forth, is unbelievably complex. And actually, there's been a lot of advancement with these new AI softwares in terms of being able to make predictions about how proteins fold, because they need to calculate how all of these waters are involved in that process. So I think the wider point is just that the important players are not always the ones that are the loudest or the most visible in any situation in nature. You know, in other words, just like with this light, right? You need to not just look at the atom that's creating the light, because two atoms are involved in creating the light, the one that's receiving it as well. The same thing could be said about the water in your body. The same thing could be said about so many, social existence is the same way. There's always people in the wings who aren't the stars of the show that are extremely critical to lifting people up. So I was actually talking about Einstein this morning with this gentleman, the physicist that I was speaking with, and we were talking about Einstein's partner on his relativity papers, who is this guy named Grossman, who nobody knows about. But Grossman was the mathematician who essentially helped Einstein create the formalizations that he needed in order to convey his ideas. So there's almost always somebody like that. And so, yeah, I think a lot of our universe and our existence is held up by these kind of invisible pieces that you have to really open your mind to considering that the most obvious solution might be only half the story in any case. Yeah.
I guess this brings up the age-old question of water wet.
It depends. Yeah.
Something that I was talking about, like, some theories that
I mean, I don't think we have enough colors to define the enormous broad spectrum that we have available to us. Like, what color is a gamma ray? You know, who knows? Probably extremely blue, but how do you get more blue than blue? I have no idea. Yeah.
You're kind of talking about like things that we can't see. I was wondering, could there be like stars that are operating at like such a, or on the scale that we can't see it? Like our color spectrum wouldn't be, is it broad enough to be able to physically see them? Or if they're like, maybe even the center is visible and the rest of it, you can't really judge the length of it?
Yes, and so the cool thing is we have instrumentation that we can view most of the electromagnetic spectrum. Whether there's a limit to that, it opens up new questions too, and I don't know, like, how big can the biggest radio wave be? I don't know. I don't know if there's a limit on that, but we're going to get to that in a moment. So we have different types of telescopes that can look at things that we can't see, and that's useful because, and I'll show you some examples here in just a few minutes, where we can actually picture stuff that's completely brilliant, but you can't see it with your eyes. So yes, in terms of the stars themselves, yes. A lot of stars are well, of course, this gets into the line between star and planet, but a lot of planets at least. And some brown dwarfs do a kind of fusion where they'll fuse heavy hydrogen, but they don't, since they don't fuse normal hydrogen, we don't call them stars. It's a bit arbitrary. But often the best way to see these cooler planet/star things is with different longer wavelength radiation, right? Infrared, radio telescopes as well, stuff like that. Jupiter actually makes a lot of radio waves himself, whatever. So yeah, you can definitely look in other wavelengths, and I'm going to show you some examples of that momentarily. I do want to make it through, I didn't totally make it through this diagram, and it is kind of important. So the important, let's just make sure you get the main takeaway here. So like stars in general, the bodies of stars, let's call it that, I think it's reasonable, give us this nice continuous spectrum. We talked about why last time. Gases, if they're excited electrically often, you can burn them, you can burn elements, they give off these individual lines. Now gases also, whatever lines they give off, they will also absorb light at those same lines. So the atmosphere of the sun does have a gaseous atmosphere to it, and it will absorb whatever elements are in that atmosphere, will absorb and create little screens, these little and we can basically pluck out what colors are missing and deduce what elements are in that gaseous atmosphere. And we can do that for all the stars. So these are our two main tools. And I'm going to tell you a little story about the couple that actually invented this. They're quite clever people. And we'll get to that in a moment. Now, there's something else that's really interesting here, too, which is captured in this diagram here. So what you see here is the wavelengths of light that actually reach down to the Earth. And what you'll notice is that most of this really dangerous high-energy light doesn't make it through our atmosphere. Now, certainly that's no coincidence, because if it did, our DNA wouldn't have been able to evolve. We probably wouldn't exist, right? So it's actually really nice that, you know, X-rays and gamma rays and all these things, for the most part, are turned away prior to reaching us. However, it means that we can't very easily set up a telescope here on Earth to view perhaps spectacular displays of X-rays and gamma rays, because I'll show you some images of X-ray telescopes here in a little bit, and you can see things that you wouldn't be able to see with visible light. Likewise, infrared light is also pretty difficult to see here on Earth as well. And so for things like X-rays, gamma rays, infrared, we actually have to set up our telescope in space in order to, like outside the atmosphere, let's put it that way, in order to actually capture anything. There is a really nice little window of radio waves that penetrates down through our atmosphere. This is convenient because we can, and I'll talk to you about the guy who stumbled across radio astronomy accidentally in a moment, but we have a little window for that. So it's kind of interesting, you know, you think this is the tiny little window that you can see with your eyeballs, right? This is the window of wavelengths that you can see. It also happens to be one of the few windows in the atmosphere from which the sun actually reaches us. So, you know, from an evolutionary perspective, it makes a ton of sense that your eyeballs evolved to see in this range, because that's the kind of light that reaches you. And perhaps your eyeballs could have evolved to see radio waves. I wonder if there are any organisms that could see radio waves. Somebody can Google that and tell me. But there's certainly, most animals, I think, essentially have evolved to deal with the fact that sunlight reaches us only in a few different wavelengths. primarily in the visible spectrum and in the radio wave. Yes?
So you're saying from like actual light that comes from the sun.
Yep.
It can be interpreted as either a radio wave and a microwave wavelength.
Well, it comes in all that black body spectrum, right? It has a peak. It has a peak to it of some color. Ours is kind of like this yellowish color. Is like its peak temperature. But all of those different wavelengths are coming. Maybe in some more than others, but the whole spectrum is coming to you. Most of it gets screened out by the atmosphere. Like all these really nasty ones get screened out. The IR stuff gets screened out. And honestly, this is a bit exaggerated from what I can tell, but most of the long wave radiation also gets screened out. So in general, the atmosphere is protecting us really nicely. And it's making it almost mandatory that our eyes are going to evolve to see the colors that we see, because those are the ones that punch through the atmosphere in a usable fashion. Is there did anybody Google it?
No animals.
No animals can see radio waves. All right. Well, it wouldn't shock me, but they're very slow too, right? So there's something about the nice thing about the visible range is that these are rather short wavelengths, so the diffraction, maybe they're more subject to vibrating the size of molecules that we have in our eyes, whereas radio waves tend to require huge antennas. You need to vibrate huge lattices, so maybe it's just that organisms here aren't big enough or molecules aren't big enough to deal with radio waves. I could see that being the case. They're always struggling with how to get the antennas more powerful, and like your cell phone and if you look at these antennas that they design, they often are trying to fold or coil up these antennas because they do need that length in order to resonate them. So it's a matter of how to pack that thing into a small space. So it might just be that of the two possible evolutionary options, the visible length was more appropriate towards the size of biological molecules. Just a theory. All right, so how do we actually look at these things? So we have a couple of places on Earth where we can look at it. We can look at the visible light. We can look at the radio light. We're going to need different instruments to pull that off. So the basic construct of the telescope, and this is all the way back to the first telescopes, like the ones that Galileo was using, they pretty much all have this same layout. You essentially take two of these lenses and you put them in a line together. So we call this opening for it the aperture, just kind of like a camera, really. It has this objective lens at the aperture. There's a big tube, and this is specified kind of by the size of the aperture. This is kind of the size of the bucket that you're catching all of that light in. And then you put another little magnifying lens at the end of it. This is going to actually serve to both multiply the first lens and also to focus the light at the end. So pretty simple idea. The problem is with these telescopes that whenever you pass, you've probably seen this with water, right? When you put your hand underwater, for instance, it sort of changes colors a little bit. And in fact, sometimes you've probably seen light go through water and maybe almost make a rainbow of sorts, right? So materials through which light passes, so solids and liquids through which light passes, have a tendency to disperse the different wavelengths. And so one way of thinking about that would be, and I don't think this is totally accurate, but it's a good way to think about it, would be that the different colors of light take different amounts of time to travel through the medium. There's a more complex phase relationship that essentially involves the relay of the light between each of the atoms inside of that. But the end product is that those different colors, they emerge at different angles from the material. And so you have a spreading of the colors. And the problem is when you try to make lenses out of glass, you end up spreading out the colors. And you actually get these kind of blurry images. Now, they're not garbage, and obviously they work pretty well. But in terms of getting a really crispy, beautiful image, you have a hard time doing it with a simple refracting scope like this, which is the basic original form of the telescope. Yeah?
Would there possibly be better improvement if we use like a digital lens.
Yes, and we're going to talk about that a bit. But people, so they did that. But before that, they tried a few other really clever ideas. I'm not going to bore you with this, but it's actually kind of interesting that all the way, really throughout the history of the Enlightenment thinkers, people were experimenting with how in the world you might be able to make a telescope, but nobody actually built one. And it was these Dutch eyeglass manufacturers who ended up doing it. I think we talked about this already to some extent. You know, one of the most remarkable things that came out of this, and we've already touched on a few of them, obviously people were making drawings of the moon, people were making, Galileo famously pointed out that, hey, Jupiter has moons too, I think that's what's happening over here, and blah, 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 it saw the phases of Venus, all this cool stuff. This was one of the more remarkable things that fell out of the invention of the telescope. This guy is probably one of my favorite scientists of all time. His name is Christian Huygens. A real interesting dude who basically, along with Fresnel, developed the wave theory of light as we know it, more or less. But he was also just, it's hard for us to imagine today the fact that these guys weren't professional scientists. Like, this guy was, I think, a physician. He did some work in civic service, right? He was something of a politician, and he just kind of did this in his spare time. Like, he just sort of noodled around with science in his spare time. Look at this telescope this guy built over here on the right. So he took the big lens and he raised it up on this big pole. I don't know if it was like a tree or a big telephone pole or something. And then some distance away, he had the tiny little focal lens. This was how he was able to get a big enough focal length in order to actually magnify and focus the image, by which, for the first time, he drew a picture of Saturn that showed that it had rings, which is really, really crazy. Now, you can get has anybody seen Saturn's rings through a telescope before? Yeah, a little bit. Pretty cool, right? If you haven't, you should right now, because they're going to disappear next year. Not like disappear forever, but Saturn's going to be turned on its side so that you won't be able to see the rings. It's another one of those things like seeing Jupiter's moons that is really just mind-bending to observe it with your own eyes. But anyway, Huygens did this. He drew a picture of it, and of course this confused people more than ever. Why in the world does this thing have rings? And that's a really good question that we'll deal with when we get to Saturn. But this is really changing how people thought about the universe. And, you know, look at this telescope, by the way. As far as crazy ideas go, that's got to be up there. Okay, so back to that aberration question. So the blurriness that you get from lenses is worth talking about for a second, because there have been numerous attempts to deal with that over the years. And it's funny because the ultimate solution is quite simple, but this is something that people tried on for a long time. They thought, well, we'll just take that dispersive effect from the first lens and we'll put a concave lens on the other side of it. And by doing that, we can redirect the distortion from the first lens and fix this to some extent. That works pretty well. It's not perfect, though. And so it's funny because people toyed around with this for years and years, but it wasn't until relatively recently that people realized you could essentially do the same thing you'd done with lenses using mirrors, right? Now, the nice thing about reflections versus refractions, so whenever light travels through a medium, like I said, it has to be relayed through all the atoms, and different wavelengths are relaying with different delays, essentially. So you can imagine as light is passing from atom to atom to atom inside of a lens, that's like a gazillion relays that it has to do along the way, right? It's one way to think about it. And each one is subject to deforming the trajectory, the path of that light, and also it's modifying, it's attenuating the frequency as well. And so mirrors don't do that at all. They're fantastic. You basically have one relay with a mirror, right? Light hits the mirror, it's relayed back in the same direction from which it came. Really, really non-perturbative, like the non-distorting way of focusing light. So this is the kind of telescope I have. They're much, much cheaper than these because they don't involve really expensive optical devices, right? You don't have to have big lenses that are polished and perfected. You just have a mirror instead. And the mirror will essentially focus the light. It will collect a good size of light. It has a big aperture, however big that bucket needs to be. It'll focus it back through a little, almost like periscope lens onto one single eyepiece, right? And you can put you can stack multiple eyepieces on these things in order to magnify it, right? Which is basically a baby version of a refracting scope that's kind of tacked on at the end. And this was a really brilliant idea for several reasons. Yeah. Well, they're easier. So has anybody played with a telescope before, like a reflecting telescope? Yeah, you have one. Cool. They're a little bit of a pain in the butt, right? Like you have to make sure that mirror is positioned perfectly. It's always getting, like if you're carrying the thing outside, and you're always kind of chasing it around, trying to get it they call it collimation, right? So that's a little bit tricky. If you have just a regular one of those telescopes, it's kind of built at the factory. It does its job. You can pull it out and do the pirate thing, and it just works. So that's nice. I don't know. I don't know if there's any other reason to use them. Mostly reasons not to use them, from what I can tell. A huge reason, it turns out, for modern astronomy not to use them is twofold. One, that those lenses are heavy. And so imagine trying to get one into space, a huge piece of glass, and you can't have it get scratched, and you don't want it to get, fogged up or messed up in any way. You don't want it to break. Glass is super brittle, right? Now, the other problem is that on Earth, gravity is a nightmare for these big guys. You have a huge lens. It tends to actually, glass is actually not purely a solid phase of matter. It's actually slightly on the liquid side too. It's slightly viscous. It will actually deform under gravity really, really quite easily. And over time, it'll deform and deform and deform. So you have, the anecdote that's always given is these cathedrals in medieval Europe whose windows are kind of dripping actually over the thousands of years since they've been 1,000+ years. I'm not sure if that's actually true, but the analogy is reasonable. Yeah.
Yeah, I just wanted to say, glass just as a thing, it's incredible. I don't know if you've ever seen the Shikuli Glass Museum up in Seattle.
I've seen some Chihulis, but I haven't seen that museum, no.
Some of the artwork, it really is spectacular about how they mold the glass.
Yeah. Yeah, I went to a glass blowing studio a while ago.
It's quite remarkable.
Yeah, it really is. It really is. It's also just those studios are incredible. It's like they're so hot. Such a sweaty way to make art. But yeah, complete respect. So, and expensive, by the way. Speaking of Chihuly, extraordinarily expensive. So manufacturing something with the specifications and the exacting let's say, tolerances necessary to focus light from distant stars is really, really, really expensive. So for all of these reasons, it turns out that the mirror-based telescope, we call it the reflecting telescope, is a much better option for almost all cases at this point. So, short of convenience, it's quite useful. Now, this is an early, from early 20th century at Mount Wilson. So they did try making these huge telescopes that were actually refracting versions, and very quickly switched over to these mirror-based telescopes. This one's 8 meters in diameter. This is down in, what is this? This is actually called, hilariously, the Very Large Telescope. Okay. Let's see here. Palomar, 5 meter on the left. I actually lifted these out of your textbook, so I won't belabor them. Another way, so mirrors tend to deform also, so they're not perfect, right? They're still going to be subject to whatever minor perturbations. And when you're looking at something that's really far away and trying to focus it, the tiniest deformation of the mirror can be a problem. One of the ways they've gotten around this is with these interesting adaptive optics, where they actually have individual mirrors, and they sort of can reposition these as necessary to account, not only so you don't have such a huge mirror that's going to deform, but they can actually hook these things up to computer software now, and they'll take into account changes in the atmosphere, which, of course, as the atmosphere is warmer or colder, you actually have, again, you're changing the properties of that material, the atmosphere material, that the light's passing through. It's changing the density. It's changing little things that are going to affect the path of the light. And so they can correct for those by actually physically moving these individual mirrors around and reconstructing the whole image. So that's pretty cool. And they've used that to make some, like this is a beautiful picture of Jupiter. You know, nothing looks too beautiful on this screen. I'm sorry about that. But they've been able to make pretty good pictures. And honestly, if you go out tonight with like your reflecting scope, you can see Jupiter. I don't know if you can see it right now. Okay. Yeah.
Like, it rises around 10 or something.
Okay, cool. Yeah, it's been too cold for me to go out lately. Kind of a wimp. But you're not going to see anything like this. And the reason is that the atmosphere itself is going to mess things up too much for you to actually pull that off. Yeah.
I understand what you're saying about how their rings are gonna go away.
So, yeah. So the ring is kind of Saturn's kind of tilted, right? And so it's tilted in such a way that we can see its rings at the moment. Yeah, so as we go through, there's alignments that happen. Saturn actually takes a really long time to go around the sun. I don't know how long off the top of my head, but a long time, many years. Now, as the Earth overtakes it in its orbit, it's going to, at some point, that correspondence between the two is going to result in that ring being perfectly on its side. And when it's perfectly on its side, it's so thin that you just can't see it. You can only really see it when it's turned towards you, essentially, or away. I don't know. I'm sorry. You have to look that up. Yeah. I don't think it'll take too long. It really just has to do with that alignment between the Earth, right? We're moving past the thing far more often than it's actually moving around us, technically. So every year, you should. I don't imagine it would take more than a year for us to get realigned in an appropriate way. But I'm just guessing. 27. A couple of years. Okay. Well, that's sad. But yeah, get your Saturn viewing in while you still can. All right. So yeah, these adaptive optic systems are really impressive for pulling off this kind of an image from Earth, which you just can't do otherwise. The atmosphere will mess you up too much. So you do find a lot of these telescopes, by the way, positioned on top of mountains, right, or in the desert where it's really dry, because of course you have less atmosphere in the case of mountains, and in the desert you have less moisture, and so you're going to have less interference. But it's very difficult to get anything approximating that picture of Jupiter from a regular telescope on Earth without some sort of ability to adjust for the interference of the atmosphere and so forth. All right. Let's see, what else do we want to say? Yeah. I thought I had one more slide here, but I guess we'll get to it eventually. So speaking of spectroscopy, this is a really cool book. I always like to recommend this to you guys. It's the history of a lot of the basic telescopy stuff was unfolding during the early part of the 20th century. And guess what was happening during the early part of the 20th century? The world was all fighting, right? So the men, generally speaking, were away fighting wars for a lot of the first part of the 20th century. And so a lot of this work was actually done by women who got no credit. And this is a fantastic book called The Glass Universe that tells the story of all these people. And so I thought I would just mention a couple of really interesting stories, because this is where we get spectroscopy from. So there was actually this couple. Let's see, it was Henry and Mary Anna Draper. This was around the turn of the century. And the Drapers were fascinated with astronomy, but it wasn't like today where you can just order off Amazon a telescope. They actually had to build their own telescopes. And they were so passionate about this, and it had nothing to do with their job, of course. Science wasn't a real job back then. These this couple, literally on their wedding nights, most people would probably have a big party after their wedding. These people went out shopping for skylights that they could melt down to make lenses for their telescopes that they were constructing, which is just absolutely adorable. Anyways, they weren't married very long, but they had been working on ways to separate, basically putting a prism in front of a telescope or after a telescope before the photographic plate and separating out the different colors of the light and trying to make sense of this. No one had ever done that before. So now Harvard was starting to put together an astronomy department at this time, and they were in the process of building some observatories there. But this work was actually done by this couple. I think that Draper, the male Draper, he was a physician, a surgeon, actually. So this was just his hobby. And so they essentially single-handedly invented spectroscopy on their own with homemade built telescopes that they did in their spare time. Now, sort of tragically, Henry got something of a really wicked cold and died when he was like 45 or something like that, suddenly. And so Mariana actually wrote to the Harvard Observatory and was like, hey, I've got all these telescopes. Do you want them? And so Harvard basically said, yeah, we'll take them. And they ended up forming essentially the basis of Harvard's entire astronomy department at the time. Entirely homemade by this couple, which is just really, really interesting. And there's another story from that book that's kind of worth recounting too, which is this idea of star classifications, this idea of standards of how bright something should be. A lot of this work was being done. So the men are off fighting mostly, I think this is World War I at the time. And so they had all of these women working in the astronomy department. Now, they were very afraid of having the women inside of the actual observatory because they thought, well, first of all, you have to have the door open all night, and it's very cold. And they're really worried that the women were, delicate and so forth. And so they wouldn't really let them in to do the observations. And so, but they needed the manpower, essentially, ironically. And so they essentially had the women working in the back, taking all of these star measurements and calculating the relationships amongst all these stars. This is really funny because the term that they used to describe these women who were working in the back rooms on all of these measurements, they called them computers, which is actually the origin of the word computer. It's actually these women at Harvard who are in the back room calculating all of these astronomical observations. And so, anyways, I would really recommend that you guys check out this book. It's really cool. The Glass Universe tells the story of all these people. They actually ended up coming up with the star classification system. It was actually a group of women who came up with that system that we still use today. And there's a really funny roundabout story. I guess we'll do part of it next semester if you guys are still here. So spectroscopy, what's that? It's just what I said. You put a prism and you split the star into its various components, and you try to make, or not just star, but like nebula and lots of the things we're going to look at, perhaps the atmosphere of a planet, you could spectrally analyze, and you try to make statements about what the actual composition of that atmosphere is. And this has never been more important to humanity because right now people are really trying to find planets that have life on them, right? So if you want to find a planet with life on it somewhere far, far away, how do you do it? Well, you need to imagine what sort of molecules life would like to have, or the converse would be what sort of molecules does life hate to have, and then start looking for the spectral signatures of those things as that planet passes in front of its star, stuff like that. So this is a really, really valuable technique. Not a ton more to say about it. It's not really any different than putting a prism in front of the objective, well, after the objective, essentially. All right, so we talked about that last time. Of course, yeah, the result of this spectrometry is that you can pull out different signatures for different stars, not too shocking. And there's a classification system we'll deal with next semester. Now, this is what I wanted to show you guys. So, does somebody have a question? Yes?
Yeah, just real quick. I don't know how much this, I guess, gets into like telescopes and like the scale of things. Like, I've always been fascinated with like one-to-one ratios all in like the world.
Okay.
But like, is there a way that you could incorporate some sort of one-to-one ratio for like the actual true size through an observable, I guess, like, is there a way to have a standardized, like, or is there?
In terms of like telescopes and magnification?
Yeah, like size of those stars and other things could.
I mean, the dimensions of them shouldn't be distorted in any way, right? Because all of the basic idea is these light rays are coming in, and what you're doing is you are not screening any of the light that's coming in. You're not turning any of it away. What you're actually doing is redirecting it so that all the light that you're getting through, your telescope aperture is now being redirected to a tiny little place, right? And so once redirected to that tiny little place, then you got one more lens there that's going to blow it back up again. So you focus all that light, which is pretty dim, but all together, when it's in one little place, it's pretty bright there, right? Now you blow that up so that you can see it, right? So there should be a true one-to-one correspondence between what you're seeing and what's in the sky. Your only limit is bandwidth, right? So in this picture here, we see Orion. Have you guys seen Orion for the most part? It's like one of the most noticeable things in the sky, as far as I can tell, beyond Venus and the moon or something. You have these 3 stars in a row. Of course, the projector's kind of crummy, but you can see Orion over there in the visible light, right? What's really fascinating, though, is if you start looking in other wavelengths besides visible. So I believe the center one is X-ray, right? So these are really, really high energy, tiny little, let's say, very, very frenetic waves of light that are coming from the same region of sky. So the exposure time is more or less the same, but the wavelength that we're looking at is much, much smaller here. Likewise, if we look in a really long wavelength beyond what we can see with our eyes, a redder one, beyond the red that we can see, in infrared, we also see a very different picture. And so what we have to do a lot of times, again, this stuff matters more next semester when we look outside of our solar system, but we're often trying to glue together lots of different wavelengths, so different, we're assembling almost collages of different wavelengths in order to make statements about the processes that are happening, because each one of these processes is reflective of something interesting that's happening. They're not just stars, right? A lot of it is leftovers from stars, or stars that have recently died, or stars that are being born, things like that. These processes that give these different wavelengths are responsible for those. So this is pretty cool. Yeah.
Speaking of Orion,
Yeah.
so I think it was last academic year. I can't remember what season it was, but there was a point when I was going to the Hawk and I looked up, and there were like a bunch of stars lined up like Orion's belt. I don't know if you know what that is, but it was like really weird.
It wasn't Orion?
No, it was literally like just several stars just all lined up.
It could have been Starlink.
Yeah, it looked like they were.
Oh, that's a satellite. Yeah, those are satellites.
Yeah, it could have been Starlink, yeah.
But yeah, Elon Musk's his like internet. What's it?
Starlink, yeah.
I was like, there they are, it's aliens, baby.
Yeah, it could have been the aliens too, I don't know. Yeah, I've seen Starlink. Yeah, it does kind of look like a string like that. Yeah, I mean, these are crazy satellites, by the way. He launches, like, what does he launch? Like hundreds of them at a time or something? They're these tiny little CubeSats. So he packs one of those rockets with like, I don't know how many, honestly, but many, many of them, and launches them all at once. So they're kind of traveling around the Earth in these swarms, basically. Yeah, it's pretty cool to see. But yeah, you can see that. You can also see the space station go around too. It goes around several times a night. So anybody seen the ISS with the telescope?
No.
Okay.
It's hard to, like, to get
Yeah. I've seen some pictures like that people have done, but yeah, it's hard to do. In front of the moon, I think that you can get a picture of it pretty good. That's the one place, but you have to have the alignment correct and everything. But yeah, Orion's an interesting situation, and we're going to talk. We'll keep talking about Orion. This isn't a class about stars, though, unfortunately, guys. I wish it was, but No, the stars are quite interesting. Also, people have been obsessed with Orion since the beginning of time. I think we did talk a little bit. We showed some interesting star maps that people had made like 20,000 years ago of Orion. There's a lot going on there. There's also a really weird mystery star there. Not to get too sidetracked, but there's this one called its shoulder, the one that's in its shoulder up there, that kind of reddish one in its right shoulder. It's called Betelgeuse. Betelgeuse has been kind of an astronomical mystery recently because it appeared to be pulsating in a really interesting way. And one of the theories for pulsating stars relates to the way that stars die and go supernova. So for a while, people were saying, oh, it's about to go supernova. This will be really exciting. Because we've only observed a couple of supernova ever. I think the last one we observed locally was back during Galileo's time. So they're very, really rare, which again, interesting that they're so rare given how many stars there are, but we'll deal with that next semester. I'm really pushing next semester hard today. Yeah.
I don't know if this is true or not. It might be just like a gag video, but I watched a scientist talk about the star or about Betelgeuse, and he was like, it's gonna explode, or it's gonna explode, and then here in like 1,500 years or something like that, it's gonna be day for 24 hours because of the light that it's gonna emit, or something like that.
Yeah, well, this apparently sort of happened in Galileo's time with a much more far away star. So supernova, if a star explodes, and it seems that they do explode sometimes. I'm not sure if they explode all the time, but that's a different story. But if it does explode, it will be fantastic for sure. It will certainly be visible in the daytime. I'm not sure if it would be bright enough to light up the sky at night completely, but it would be fantastic. But people have been kind of modifying that. So it didn't explode when they thought it was going to explode, it seems like. So people have been trying to come up with other explanations. I've heard all sorts of things. The most popular one today is that there's actually more than one star there, and that it's kind of being yanked around, right? There might be 3 stars even. And so you're actually seeing it kind of coming in and out of focus, something like that. I don't know. This is, again, my theory would probably come down to the actual lattice structure of my favorite theory would probably be like, hey, we don't understand what the structure of that star is, and that if its structure is changing in some way due to, changes in its fusion processes or otherwise, it might change how bright the thing looks as well. So that's a possibility also. Yeah. It's kind of a crummy picture, I'm sorry. It's up in the shoulder. So if we think about Orion's belt being the 3 down here, it's like up in the right corner of this picture. It's a really bad photograph of Orion, I'm sorry. Yeah. We'll come back to Orion, especially if you're around next semester. All right, so the result of this, oh, yep. No. Yeah. I am not prepared to deal with black holes today. I'm skeptical of these entities, let's put it that way. Again, if you don't understand, if you think something that's dim, the only way it can be dim is if it's far away, then you've never seen a bicycle half a mile away on a country road before, right? That's my way of looking at it. It's like if you don't have a way of separating out the different reasons why something could be dim and have a lot of mass to it, then you could be missing a huge part of the story. So I think, I'm going to deal with this in so much detail next semester, but I think personally it's our responsibility as scientists that before we start inventing new forms of matter that defy our standards otherwise, that we should consider all other possibilities for what could be causing the phenomenon before we start inventing new forms of supernatural materials and stuff like that. I would say that history has proved out that whenever we do that, it turns out to come back and bite us in the butt, basically. And there are numerous examples where we have magical substances that turn out to have much more mundane explanations. I think I pointed out heat being a really interesting one, right? It was treated as this kind of magical fluid that was hidden inside of materials that would transfer from one object to the next. Obviously, we came to understand that that wasn't the case. but it was very much a sort of dark material for a while. Heat itself was this dark fluid that couldn't be bottled, but it could be detected. And it was obviously flowing because the equations showed that it obeyed heat flow equations, which it does nicely. Turns out a lot of things obey heat flow equations, including diffusion, entropy. A lot of things obey heat flow equations that aren't fluids, right? So yeah, it's too big of a puzzle, and I want to be sure that I kind of give the devil its due and make sure we understand all of the observational data surrounding black holes before I punch them into oblivion. Yes? You had another question? Yeah. So there's a lot to say about black holes. Again, I'm really pumping up next semester. I actually think next semester is kind of like the real gem of this entire experience. So just because there's so much on the move in those disciplines. Cosmology itself was not even considered a real science until about the 1960s. So it's like one of the youngest sciences in existence, you know. Perhaps if you consider computer science a science, perhaps that's also very young, but neuroscience maybe too. There's a few of these places where we're basically babies when it comes to our scientific understanding of what's happening. And so the stars and cosmology are two of those. So it's a really exciting place. All right, so look, when we look at something incredible, right? And what do we have a picture of here? I must have written this down. Good man alive. Well, needless to say, it's some sort of nebula. I think this is the Crab Nebula, actually. What's interesting is that we see different structures emerge when we look at it in different wavelengths, right? So the UV image that we get is very different than the radio image, from the infrared, from the visible image, right? The X-ray run's really fantastic because you see this almost like vortex structure emerging from it. And we'll get into the different theories for what this object could be next semester. But needless to say, we need all of these different wavelengths in order to make sense of it. Infrared, by the way, is a really interesting one because infrared radiation is quite ever-present in our daily lives. It's associated with heat, right? And so it's often used for really cool optical processes when people are trying to see through buildings and stuff like that. Like really cool or really creepy, it's up to you. But yeah, with infrared, you can actually sort of, it has a tendency to travel, to be relayed very pristinely through objects, which is quite interesting, right? Different wavelengths have a tendency to be relayed or not relayed through objects, depending on their properties. And we talked a bit about radio waves, right? But infrared seems to travel through objects really nicely. So infrared. Okay, radio telescopes. This is kind of interesting. This is a story worth telling. So there's radio waves were actually, we talked about how Hertz had essentially realized that electromagnetism could be coupled to generating through light, essentially, through radio waves, could transmit energy at a distance, let's say. You could excite this little ring structure. You could create sparks in this little coil on the other side of the room. Very quickly, people became interested in this for communication, obviously. So one of those, there was a number of big corporations that emerged, closely linked with different military industrial groups. One of them was Bell Telephone Laboratories, who became very interested in this in the early days, long before cell phones. And there's this guy, what was this guy's name? Karl Jansky, who was working back in the 30s on some primitive forms of radio communication. And he made a really interesting observation. There was this noise. See, this was his radio antenna that he was building. It's very huge and cumbersome, as radio antennas often are, like I was saying. And he made this observation of this noise that kept occurring inside of his radio antenna. Now, the weird thing about his noise signal was that he noticed it coming every day, what was it? Just before sunrise every day, which was really, really interesting. So, you know, he started to refine that a bit more, and he noticed that I believe that he noticed that it was actually coming something like 4 minutes before the sunrise every day. Now, if you think back to the difference between the solar day and the sidereal day, right? So the time that it takes for you, or me, or us sitting here on Earth to be turned around and facing the sun is a little bit longer than it takes for us to be facing the same actual point in the sky with respect to the background stars, right? Does that make sense? We talked about this earlier. So you're turning, but because the actual Earth is orbiting at the same time, it's sort of stepping into the frame a little bit. You have to turn a little bit further back to face the sun each day, a little bit further than an actual day with respect to the background stars. So what he realized as a result of this was, hey, I think that this source of noise, this static on my radio antenna, is coming from the stars, actually, right? Because it was showing up at this point right before the sun would rise every day, because it was coming back to that same point in the sky every day, which is just a really interesting leap of insight. So people very quickly realized that you could get information from stars, not all of them, but from various places in the sky that were in the radio frequency of the spectrum. And people have, taken this to the nth degree and made incredible images as a result of it. They built these huge dishes to pull this off and huge arrays of it. They get these incredible images. This is some sort of a strange gas jet that's being ejected from, this is actually a galaxy that's at the center. So if you were looking in the visible range, you'd see a little spiral galaxy there. But you see these huge jets being ejected from the center of this galaxy, structures that are much more massive than an entire galaxy, and they're only visible in the radio frequency spectra. So we don't need to belabor that. Another way that they can make these images even more pristine is by setting up huge arrays of these telescopes, right? And this is kind of like triangulating a source, right? So if you set up a bunch of different telescopes, you can actually kind of piece together the information that you get from each of them to even more closely focus in on a point. And you assemble all these images in such a way that you can get, pictures like that one that I just showed you of something that's extraordinarily massive. And you get very detailed images as a result. So they call these arrays. Here's another array. This is down in the Atacama Desert in Chile. There's another kind of telescopy, which is called radar telescopes. And I guess this is where we'll end up for today. This is recently defunct telescope, but it's kind of a similar idea to, these are actually useful for looking at the motions of things. Have you guys anybody ever gotten a speeding ticket before? Yes, me too. Especially when I used to drive a motorcycle a lot. They're very hard to drive under the speed limit. But the cops have these little lasers that they shoot at you, right? And so this is the exact same principle, where what you do is you shine some light off of a distant object and wait for it to come back, and you look at the difference in that wavelength as it comes back. And so radar telescopes. There's a couple more I'm going to go through next class, but I want to let you guys get out here on time, and we'll pick up with our story. Yeah, come talk to me. Yeah, if you want to. If anybody has more questions.